So when we finished chapter 2, we were looking a lot like a math class, and we were doing a lot of calculations and converting between units, and that's a very important part of science in general. But this chapter we're going to start to look a little bit more like chemistry, and so we're going to talk about what matter is, and its characteristics, and we're also going to talk about energy. So the energy part at the end is really the energy of chemical reactions that we're typically talking about. And we're going to talk about how we can calculate some of that or measure some of that. But in the first part, we're going to do a lot of descriptive chemistry, a lot of understanding about states of matter, chemical changes, and physical changes. So let's go ahead and get started with what is matter. Okay, so matter is anything that occupies a space, okay, and has mass. And we've talked about, and you'll be looking at the density equation today in the lab. We know that density is equal to mass divided by volume. And the way my wife remembers it, she teaches to her students density, right? So you can draw a heart like this. Density breaks your heart like that. And it's the M over V that you get when you draw the line through the middle. Typically, the units for mass are in grams, and the units for volumes are in milliliters, especially in chemistry. In physics and in engineering, it's often kilograms per meter cubed. But those two numbers are interconvertible. You learned how to do that in the last chapter, right? So all of matter is made up of atoms. Okay, so there's this shirt that says never trust atoms because they make everything up, right? Well, that's because everything is made up of atoms with the exception of energy, and that's the other part of this chapter. So atoms are small. So on the scale, sorry, it's a little windy because there's a ceiling fan up there. On the scale of meters, they're about 10 to the minus 10 meters. So think about what that means, right? That's 0 point and then 0, 0, 0, 0, 0, 0. Wait, I can't do this right. 3, 4, 6, 9. I think I got this right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, so I got one too many there. 10 to the minus 10 meters in length. So that's pretty tiny, right? Hydrogen and helium are even smaller. They're the two smallest elements on the periodic table, and I'll pull up a picture of the periodic table in a little bit. A speck of dust is 10 to the minus 4 meters roughly, so 10 million times the size of an atom. So a speck of dust, when you see like the little mote that floats around in the air, that little guy is about 10 million atoms wide. If you think about that little dust speck that floats around the air that you can see. And if you think about the volume, right, it's 5.2 times 10 to the 17th atoms in that little speck of dust. So atoms are really small. They're hard to see. We can't see them with the naked eye, but we can image them using modern spectroscopy or microscopy methods. We can actually see the outlines of atoms with the modern microscopes. Okay, so then atoms are the smallest unit of matter. Well, and there's subatomic particles, but of the type of matter that we see every day. Atoms are the smallest unit of that matter. And if you can combine atoms together, that's when we get what we call compounds, okay? And you can guess from the name that compound means it's made up of two or more types of atoms. And so we write these compounds, right? These and for many of them, that's what we call molecules. But molecules, molecules are can be a type of compound that consists of two or more elements combined together. So water, H2O, we're really representing a molecule of water. In that formula, the subscript refers to the number of hydrogens. So the subscript has to do with the atom to the left of it. And there's a subscript here, and like in math, when you like multiply something by 1, you don't have to write it because it's sort of redundant. It's there, right? So in chemical formulas, since we're writing the O, right, like this, then what that means is there's got to be one of them, otherwise we wouldn't have written it. So we leave the one subscript out all the time. So the subscript following the symbol is the number of units to the left. Now, in this context, these are atoms, okay? But just like in math, you can have parentheses. You can have parentheses in the chemical formula, and that subscript represents everything in that parentheses. So, for example, oh, by the way, that was H2O, right? This is barium nitrate. You'll be using it, I believe, in your lab today. So, barium nitrate. You'll notice that there's one barium, because you think about the subscript 1 there. Let me blow that up a little bit. And then inside the parentheses, there's a nitrogen and 2 oxygens. That's what that means, because there's a 1 here too. Again, we don't write that, but we know that that's there. And then out here, you notice there's a subscript 2. So this subscript 2 multiplies everything inside those parentheses, like this. Okay? Just like it would in a math equation. So what does that mean, right? Well, what that means, if I were to count each type of atom, I have 1 barium, and then I have the 2 applies to the nitrogen, right? So I have 2 nitrogens, and then I have 4 oxygens. So in that formula for barium nitrate, there are actually a total of 7 atoms in that formula. Let's see. Yeah. And then, so why don't you try this, right? Look at these formula, and then we'll do like this, C and O. And then this one's C, H, and O. And I'm just writing them in the order I see them across in the formula, C, A, N, and O. And what I want you to do for each one of these is to identify the number of each type of atom in that chemical formula. I'm going to pause the video. When I come back, the answers will be there. So this is what we ended up with for the chemical formula, from the chemical formula. There's one in CO2. There's 1 carbon and 2 oxygens. For methanol, this is actually the compound methanol. It comes from a heating wood, so it's often called wood alcohol. But methanol, it has 1 carbon, 4 hydrogens, because you combine these 2, right? And then 1 oxygen. And calcium nitrate, if you got anything wrong, I'm going to guess that some of you might have put 2 calciums there. But the subscript only applies to the stuff in the parentheses. So if you got 2 calciums, you have to be careful not to just think that this applies to everything to the left. Because there's like a plus sign in between the calcium and the nitrate there, if you think about it like it's a mathematical equation. So there's 1 calcium, there's 2 nitrogens, and 6 oxygens. Okay, so let's talk about other ways that we can classify matter. Okay, so matter can be classified according to its composition. And what I mean by that is you can have pure substances, and then you can have mixtures, okay? So in a pure substance, what do you think of when something's pure, right? We think of homogeneous sometimes, but what we should be thinking about is all one kind of unit. So, for example, a pure substance is 1 type of atom, or, not and, or 1 type of molecule. So you could have, for example, pure gold. Now the elemental symbol for gold is AU, okay? And if you have pure gold, it's composed entirely of gold atoms. There's nothing else in there. So that's 1 type of atom. On the other hand, if you have an ice cube and it's well frozen, right? The only thing that's in there is H2O. So this is a pure substance has just 1 type of atom or 1 type of molecule in it. Now, when we talk about pure substances, right, we can classify it as either being elements, that's what this is, or compounds. And remember, I just mentioned earlier, compounds are 2 or more elements combined in a fixed way, like H2O, for example. We say that's in a fixed proportion. They're always in the same ratio. So I wanted to point out that elements could also be further broken down as being atomic or molecular. Most of the elements by far are atomic elements. That is that when we're talking about a pure substance, right, it's made up of one kind of atom, and those atoms are all individual units. So gold, for example, or sodium, or let's see what other things would be commonly, like calcium atoms or iron, those would all be atomic elements. They exist as individual atoms. Okay, and then there's ones that are molecular. Now, remember when we talk about a compound, we have again H2O, right? It's atoms in a fixed proportion together. But in molecular elements, what we have is atoms that are together, but the same type of atom. So you may not know this. Like when you go breathe in and you're breathing air, you have oxygen going in, right, and nitrogen going in, and when you exhale, carbon dioxide and water come out, right? Well, when the oxygen is going into your lungs, it's not just oxygen atoms, it's actually O2. And nitrogen is actually N2. And there's actually a list of 7 of them. We'll talk about those later when we start naming compounds. But I wanted you to get the idea that not all elements are individual atoms. Some elements are molecular in nature, and some of them are kind of weird. But there's only about, I don't know, 8 or 9 molecular elements, and the rest of the elements on the periodic table are all atomic. Here's a fairly nice periodic table that you can find on the internet. It's called P-Table. I don't know. I think it's free, right? I mean, it's ad-free, I think. But it's a fairly nice periodic table. And what you'll notice is, if you look on this periodic table, you can see. I'll get this mouse here. There's hydrogen, right? It'll pop up in the window right here. And then there's beryllium. So each one of these, okay, is a different kind of element. So if you look on the periodic table, you can go all the way down to here, and we get to element 118. So there's 118 different elements. Now, naturally occurring elements, there's not as many. The last naturally occurring element is actually, let's see, might be radium. No, uranium. Take me a second to figure it out. It might be, of the stable isotopes, it's bismuth. But there's a lot of naturally occurring radioactive elements that are a bit further down the periodic table than bismuth. Yeah, I think uranium, neptunium might be the first man-made element. But anyways, that's really not that important. I just got a little carried away. These are all different kinds of elements, and there's a lot of them. I expect there's a list, and it's actually posted already, but I don't think it's available to you. There's a list of elements I expect you to have sort of memorized, and really by memorization, I just want you to have the names and the symbols for those elements. So many of them you're familiar with, like sodium, for example, Na, right? See if I can have it stay there. No, can't get it stay there. Sodium is one that you're familiar with. Now it's Na, like I said, so it's a little harder to remember. But magnesium is Mg. Potassium is one of the hard ones because it's K. And then there's calcium. So there's a number of different elements on the periodic table, and I have a list of ones that you have to have memorized their names and their symbols. So in addition to pure substances, we also classify things as mixtures. Okay, and those are either homogeneous or heterogeneous. So when I say it's homogeneous, it's uniform throughout. So if you take, for example, and you make tea, right? And you take a tea bag and you put it in the water and it turns brown, right? And that color, it's clear. There's not like things floating around in it. Coffee is the same way. It's a homogeneous mixture. That is, it's made up of a lot of different things. There's hundreds of different things in coffee, for example, but it's homogeneous. It's uniform throughout, and part of the way you can tell that is when you look through it, it's clear. Now, you can also have things that are heterogeneous, right? A heterogeneous mixture would have irregularities in it. So if you drink boba, for example. I've never actually had any, but it looks gross to me. But anyways, if you're drinking boba, right, there's those floaty balls or something, those gelatin things that float. That's a heterogeneous mixture. It's not uniform throughout. If you're eating beans and rice is a heterogeneous mixture. So I wanted to do, there's two exercises on this page. There's this stuff that's over here, okay? And I want you to identify those as pure substance, homogeneous mixture, or heterogeneous mixture. Okay, and then we'll break it down some more after we sort of classify it as that. So we want pure substance, homogeneous, or heterogeneous. And then we'll break down pure substances in a little bit, okay? So let me pause the video, and then I'll sort of put marks by each one so you can tell which is which. So that's how I would classify those. Mercury in the thermometer would be the element mercury. It's pure. Exhaled air, we talked about that already, right? It's nitrogen and oxygen going in, it's carbon dioxide and water going out. But normally when you breathe out air, you're not seeing like junk floating around, right? So it's the gases, the air from your lungs is a homogeneous mixture. And then chicken noodle soup, of course, is heterogeneous. Got noodles and chickens and vegetables and stuff. And then sugar would be a pure substance. Now, sugar, when we say sugar, like table sugar, it's C12H22, I believe, O11, right? And then mercury, the symbol for mercury is Hg. So you could further classify these as an element or as a compound, right? And so mercury would be considered to be an element because there's just one kind, but table sugar, what we call sucrose actually in chemistry, is a compound because it's made up of carbon, hydrogen, oxygen, but always in those proportions. Now, another skill I'd like you to have is to be able to identify whether or not a panel of pictures like the one shown to the right are mixtures or pure substances. Okay, so what I'm going to do is pause it and let you decide, and then we'll talk through those. So the top one is a pure substance. Now, you notice it's made up of two dark atoms and one light atom. This is also, this middle picture, panel B, is also darks and lights. But you notice here they're combined in the same proportion always. Here they're separate atoms. So this is a mixture of atoms. This is a pure substance. And this one is a mixture of elements that are molecular. So for example, like nitrogen and oxygen, or other gases like the other diatomics, which we'll talk about later. Okay, so pure substance, this would be a mixture because you see separate individual types of atoms, and this would also be a mixture because you see separate individual kinds of molecules. Okay,